Okay, shall we make a start? Welcome back to Dynamics, and for those watching online, welcome. So last week we started to study constrained dynamics, and in particular we were looking at the motion of a point particle that's acted on by the force of gravity, where the particle is then further constrained to move along a particular curve or surface in R3. We looked in detail at the example of a simple pendulum, and there the pendulum constrains the particle to move on a circle in a vertical plane. So that's an example of constrained motion on a curve, namely a circle. In today's lecture, instead, I want to look at constrained motion on a surface. So you might imagine this as modeling, say, a small bead that's free to move on a nice, smooth, frictionless surface. And for simplicity, we're going to take that surface to be a surface of revolution. So we start the lecture today by reminding ourselves what a surface of revolution is from the geometry course last term. All right, so I'm going to start on the right-hand board today because I'm going to draw a picture and then refer back to the picture throughout the lecture. All right, so we study a particle moving under gravity on the smooth inside of a surface of revolution. So underline that, i.e. a surface defined by Z is capital H of R, where R, theta, and Z, that triple, are cylindrical polar coordinates. Okay, so I remind you, cylindrical polar coordinates. Z here, that's the usual height coordinate measured vertically upwards from some origin O. And then R and theta, they denote polar coordinates in the horizontal XY plane. And I'm going to draw a picture of that. So if you're going to draw this picture, then try and draw it big, because there's quite a lot going on in the picture. So the Z-axis runs vertically up the board. That's the upwards direction. And then I'm going to draw the y-axis horizontally this way. That's y. And then the x-axis runs this way. And the axes intersect at the origin O. So this is the xy plane down here at z equals 0. Remember that the r coordinate in polar coordinates, that's the horizontal distance of points from the origin O in the xy plane. So that means if I draw this straight line here in the xy plane from the origin to another point, the length of that line is r. And then the theta coordinate in polar coordinates is measured this way. So theta equals 0 is the positive x-axis. And we measure theta in the anti-clockwise direction in the xy plane as viewed from above, as in the picture here. Okay, so next I'm going to draw my surface of revolution on this picture, and I'm going to draw it in blue. All right, so it's like that. Okay, so that's supposed to be a surface. And the height of points on this surface, so the height, Z, is given by capital H of R. So this function capital H, that's going to determine the shape of my surface of revolution. Now, if you look at the set of points in the xy plane that are at a constant distance r from the origin, that's a circle of radius r in the xy plane. And the height of points on my surface, they depend just on that radius r of the circle. So that means that all the points on the circle of radius r, they all map to the same height. That also means then that if I cut my surface with a horizontal plane, so at some fixed height, then the cross-section of the surface is always a circle. It's a circle of radius r, where the height z and the radius of the circle are related by this equation. That's also what makes this a surface of revolution. So it's invariant under rotating the surface about the z-axis. And those rotations about the z-axis, they precisely shift the theta coordinate here by a constant, and that rotates the circles that are the horizontal cross-sections. So let me write that as a remark underneath. So RMK remark, the surface is invariant under rotation about the z-axis. Okay, next I'm going to draw on my point particle. So that's the blob there, that's the point particle that's going to move on the surface. And then I drop a perpendicular down here. So that's a right angle from the line between the particle down to the xy plane. Then next I'm going to introduce an orthonormal basis for these cylindrical polar coordinates. So Ez is a unit vector pointing vertically upwards along the z-axis. In previous lectures I've called that vector k, but at least for today's lecture Ez will be a unit vector pointing vertically upwards. That's Ez. And then for my basis vectors in the horizontal plane, I'm going to use polar coordinate basis that we introduced in the lecture last Thursday. So you might remember that that is ER, which is a unit vector pointing radially outwards. So again, if I continue that line here onto the z-axis, that's a right angle. And moreover, the length of that line there is precisely this distance r. And then finally, E theta is a unit vector that's perpendicular to that in the direction of increasing theta. So Ez, Er, and E theta, they're unit vectors and they're mutually perpendicular, so they form an orthonormal basis. And I can then use that to write the position vector of my particle. So the position vector, so that's a vector r of the particle, is scalar r er plus z ez. So scalar r er, that's the position of the particle in the horizontal plane, and z ez gives its height. And finally, the last thing to draw on is the forces that are acting. So we're told here it's moving under gravity. So that means it will have a weight, mg, acting downward. So m is the mass of the particle, little g acceleration due to gravity, as usual. And then there must be some kind of contact force between the surface and the particle. And I'm going to draw that contact force just going this way. And that's going to be vector n. That's the push of the surface on the particle, the contact force. Right, any questions on the setup so far? Is that clear? Do you want to ask anything? Okay, so we can now write down Newton's second law for the particle. And so mn2 is Newton's second law. The mass of the particle, little m, times acceleration, vector r double dot, is the total force acting. That's vector f. And there are two forces. There's gravity, so that's minus mg times Ez, and then plus the contact force N. The next step is to write acceleration here in terms of our cylindrical polar coordinate basis, and we can do that using the results from section 4.1. So that's earlier in the course. So that allows us to write the left-hand side as mass, and then in brackets, so it's scalar r double dot minus r theta dot squared, ER, plus 1 over r d by dt of r squared theta dot e theta plus z double dot Ez. So that's the left-hand side here of the equation. In particular, in the square brackets, that's just acceleration in cylindrical polars. So to compute that, when I take r double dot here, well, I need to take two time derivatives of this first term, RER. And that's precisely the first two terms that I've written here. And we derived this expression for acceleration in polar coordinates in Thursday's lecture last week. And then finally, taking two time derivatives of ZEZ. Well, Ez is just a unit vector pointing upwards. So that's Z double dot Ez. OK, so that's the left-hand side. And on the right-hand side, we have the total force acting minus mg Ez plus N, the contact force. All right, so that's a vector differential equation. It's not immediately obvious what to do with it. So you might decide to write it out in Cartesian components. But just as in the example of the simple pendulum that we looked at last week, we should be a bit smarter about what it is that we're actually trying to do with this equation. What do we want from it? In particular, if we're not interested in working out what this contact force N is, we can immediately eliminate it from the equation by taking a dot product of this equation with a tangent vector to the surface. That's exactly what we did for the simple pendulum last week. And this is a surface of revolution, and there's an obvious tangent vector. So remark, RMK, E theta is tangent to the surface. And we can see that from the picture here. E theta, that's this direction, that's always tangent to a circle of constant radius in a horizontal plane, and so it's also tangent to the surface. So that's the first remark. And the second remark is that we're told that it's a smooth surface in the preamble at the top there. So it's a smooth surface. That means physically that there's no frictional force acting. So if and only if no friction. And last week we said that that means that the contact force N is perpendicular, or equivalently normal, means the same thing, equivalently normal. So N is for normal to the surface. So as we were discussing last Friday, if I had any component of my contact force that's tangent to motion along the surface, then physically that would have to be some kind of frictional force or resistive force of the surface on the particle. So when we say it's moving on a smooth surface or a frictionless surface, geometrically that means that my contact force is perpendicular to the surface, or in other words, there's no component tangent to the surface. And so I immediately deduce that N dotted into E theta is 0. So E theta is tangent to the surface, N is normal, so their dot product is 0 and they're orthogonal. Okay, so that's the key point. If I now take Newton's second law above and I dot it with E theta, well, E theta is orthogonal to ER, and it's orthogonal to EZ, and so also to this term, and it's also orthogonal to N as well. So the only term that survives when you take the dot product is this one, proportional to e theta. So we immediately deduce that 1 over r d by dt of r squared theta dot is 0. So obviously we can multiply through by r here, and then this is just saying that r squared theta dot is independent of time. It's a constant. So r squared theta dot, and I'm going to define that quantity to be little h, and we've just deduced that it's constant. We met this quantity little h briefly earlier, and there it was related to angular momentum. And that's also true here, and we can see that by computing the angular momentum of the particle. So let's compute the angular momentum of the particle about the origin O. So the angular momentum, that's a vector, L. It's defined as r, that's the position of the particle relative to the origin O. And then you take a cross product with the linear momentum of the particle, and that's just mass times its velocity, r dot. That's the definition, and then I can substitute in here for my these quantities in terms of my cylindrical polar coordinates. So that's mass, and then in brackets, scalar r e r plus z e z. That's position in cylindrical polars. And then for the velocity in cylindrical polars, that's scalar r dot e r plus r theta dot e theta plus z dot e z. So the second term here, that's velocity in cylindrical polars, in particular the first two terms. That's just components of velocity in the horizontal plane. And again, we derived this formula in polar coordinates last week. And finally, the component of velocity in the z direction, that's just z dot ez. Okay, and if you now multiply out those cross products and simplify, you get the following. So there's an overall factor of the mass, and then r squared theta dot ez plus z r dot minus r z dot e theta minus z r theta dot e r. And in deriving that line, I've used, so using er crossed with e theta is ez, and I write plus the cyclic permutations of that equation. All right, so what did I do to get this line here? So there's a cross product of two vectors, and I've just expanded that out. So I have ER here crossed with ER. That's 0, because the cross product of a vector with itself is 0. But then I've also got ER crossed with E theta, and I've used that that's equal to EZ. Again, we've seen that equation, that particular cross product, before in previous lectures. So that gives you this term r squared theta dot ez. And for the remaining terms, you can use the cyclic permutations of this equation. So also E theta crossed with Ez is ER, and Ez crossed with ER is E theta. And those just follow by writing out the original definitions of these vectors in terms of Cartesian coordinate basis I, j, and k. All right. Any questions on that so far? Is that all right? All right, following. Good. So we see, if you look at that, you see that if you take L, the angular momentum about the origin, and you dot with Ez, that just picks out the first term. And that's m r squared theta dot. And that's exactly m little h, where I introduce little h as r squared theta dot above. And we've just seen that's constant. So i.e., we have shown the component of angular momentum, L, along the axis of symmetry that's the EZ direction, is conserved. So that is, it's constant when evaluated on a solution to Newton's second law. So by the way, the other two terms here in the expression for angular momentum, they're not constant in general. There's nothing particularly special about those components. All right, so we've extracted one component of Newton's second law so far, and it's good to take stock at this point and again think about what are we trying to do in the problem. So I'll write this as a remark. So note that Z is capital H of R. That just defines the points on my surface of revolution. So given R of t, we know Z of t. Okay, so Z of t is just H of R of t. And geometrically here, this scalar R of t, it's just this distance here. It's the horizontal distance of my point particle from the z-axis. It's the length of that dotted line. Okay, but also we've just shown that d theta by dt is h over r squared of t. Okay, so that's this line here. If you just write theta dot here and take the other two terms to the right-hand side, get theta dot is little h divided by r squared. So again, so given r of t, we just integrate that equation to get theta of t. Okay, just by integrating, taking the dt to the right-hand side and integrating it, we get theta as a function of t. So in other words, if I know this scalar function r of t, then I know z of t, and I know theta of t, so I know exactly where the particle is, and I've solved for the dynamics of the particle. So this implies that we want an equation of motion for this function, the scalar r of t. And on general grounds, we expect that to be a second order ordinary differential equation. As for the simple pendulum example last week, we may extract this so the equation of motion we're looking for from Newton's second law N2 dotted into vector little t, where this vector little t is another tangent vector to the surfaces. Okay, so we've already dotted Newton's second law with one tangent vector to the surface, but it's a surface, so there are two tangent vectors. In general, the position vector of my particle, remember, so the position vector r is scalar r er plus capital H of r ez. That's the general position of my particle. And if I come over here and again look at my picture, if I fix some constant value of theta, so let's say theta equals pi over 2, so that I'm along the y-axis here, then as I vary scalar r in that last expression for position, I precisely move along some curve up here like this on my surface. Okay? So if I then want a tangent vector along that curve on the surface, I just have to differentiate with respect to this parameter r. You learned that in the geometry course last term. So this implies the tangent vector t that I'm looking for is when you just take the derivative d by dr of the position vector r above. So here, er is just a constant unit vector. And if I differentiate r with respect to r, I get 1. And then plus h dashed of r, ez. And here, so here a dash will denote derivative with respect to the argument r. So that's another tangent vector to the surface. And so I can take Newton's second law again and dot it with this tangent vector t. Well, Newton's second law has disappeared off the top. Oh, it's a long way off the top. I won't try and find it again. So ER and EZ are both perpendicular to E theta. And they're also perpendicular to the contact force N. So quite a few terms drop out when you take the dot product. And you get M, and then in brackets R double dot minus R theta dot squared plus M H dashed of R Z double dot is minus mg h dashed of r. Okay, so that's what you get by dotting Newton's second law with that tangent vector. And then following our remark above, we can substitute for theta dot. So theta dot is little h over r squared. So I can substitute that in for theta dot squared in the line above. And moreover, remember that z is capital H of r. And so then by the chain rule, that implies that z dot is h dashed of r, r dot. And similarly, I can compute z double dot by taking another time derivative. So that's h double dashed of r, second derivative of h with respect to r dot squared, plus h dashed of r double dot. So that's the chain rule that we've used there. Okay, so we can substitute for theta dot into the line above, and also for z double dot into the line above. And if you do that, you get the following. So in brackets 1 plus h dashed of r all squared, close bracket r double dot, plus h dashed of r, h double dashed of r, r dot squared, minus h squared over r cubed is equal to minus little g h dashed of r. And as promised, so remark, that's a second order ODE. It's a second order ODE, ordinary differential equation, for r of t. All right, it's not a very nice looking equation. The equation, of course, depends on the choice of surface of revolution, and the choice of surface depends on this capital H of r function. But even for quite simple choices of that function, this is a pretty nasty differential equation, and we're not going to be able to solve it in closed form in general. But given a differential equation, there are always certain things you can do with it. So you might be able to deduce some general properties of solutions of this equation. You might be able to find approximate solutions, or you can just stick it onto a computer and solve it numerically and see what the particle actually does. However, rather than do that, I instead wanted to take a different approach. So also last week, we were discussing conservation of energy. And in particular, we showed that for a particle moving under gravity, moving along a smooth curve or a smooth surface, there's always a conserved energy. That's the first point. And the second point is we expect that to give a first-order differential equation rather than a second-order differential equation. So let's see that that is the case. So there's a better approach. Than just trying to tackle this second-order equation directly. And that's to use conservation of energy. And that was in section 5.1, so from section 5.1. So that was quite a general analysis, and we deduced that E, the total energy of the particle, so that's defined as T plus V, where T is kinetic energy of the particle, and V is the potential energy. So that's the definition of E. And so the kinetic energy is a half m, and then modulus of r dot squared. So that's the speed squared of the particle. And the potential energy here is the gravitational potential energy. So that's m times g times z, with z the height. So that term there is the gravitational potential energy. And we know that's constant. That was a result that we derived last week. So we can compute more explicitly what this quantity is. So I want to write out this speed squared in terms of my cylindrical polar coordinates as a first step. So modulus of r dot squared, that is defined as r dot dotted into r dot. And that's scalar r dot er plus r theta dot e theta plus z dot ez. So modulus squared. And so when I take the dot product of that vector with itself, remember that er, e theta, and ez, they're all perpendicular to each other, and they're all unit vectors as well. So actually, this is just the sum of squares of the coefficients when you write this out. So it's very simply, it's just scalar r dot squared plus r squared theta dot squared plus z dot squared. Sum of the squares of the coefficients. Okay, and then just as before, we can substitute for theta dot. So it's up there is h over r squared. And also z dot is h dashed of r dot. So we've had those equations already above. So if you substitute all of that into this conservation of energy equation here, we get that E is equal to a half times the mass. And then we get scalar r dot squared plus, and then for r squared theta dot squared, I can substitute for theta dot here. So that's little h squared over r squared. And then finally, z dot squared from here, that's h dashed of r all squared, r dot squared. Okay, so that's the kinetic energy term, plus mg, and then z is precisely capital H of r, and that's constant. And as promised, that is a first order ODE for r of t. So remark, a first order ODE, ordinary differential equation for r of t. Okay, so if you take d by dt of this equation using the E as constant, I will get r double dot terms on the right-hand side. And you can check, if you want, that the equation that you get is precisely the equation of motion with r double dots in. That's up here from Newton's second law. Another way to say it is, we've effectively integrated Newton's second law once to obtain a first-order equation rather than a second-order equation, where e here on the left-hand side is an integration constant. Okay, so the first-order equation here is some function of r, and r dot is e, which is a constant. It's a first-order equation, though, so in principle we can integrate this, but again, we won't be able to do the integral explicitly and find the solution in closed form. However, we've now seen many times in the lectures that using conservation of energy, we can deduce some qualitative features of the motion and also some quantitative features of the motion too. And so that's what I wanted to demonstrate to you in an example. So let's actually look at a particular example of this. So it's motion on a paraboloid. All right, so I'm going to choose a particular surface now. So remember that z is capital H of r, and I'm going to take that to be r squared over 4a, with a some positive constant. So z is r squared over 4a, that's a parabola, and the surface of revolution that you get looks pretty much exactly like the one that I've drawn. So that's why I drew that particular surface. That looks pretty much like what that surface looks like. So the particle is initially at a height z equals a, at height z equals a, and is projected horizontally with speed little v. And our problem is to show the particle moves between two heights. Show the particle moves between two heights. In the subsequent motion. All right, so this is an initial value problem. We're given the height of the particle initially and also its velocity initially. So initially, z equals a. On the other hand, we also know that r squared is 4az. Okay, just by inverting r squared here in terms of z. And so since z is a initially, then r must be 2a initially. Remember that r is positive, so when I take the square root here, I take the positive square root to get r is 2a. And then we're also told it's projected horizontally at speed v. That tells us that r dot is v e theta initially. So again, if you look at the picture, so it's at some height z equals a, say this height, and if it's moving horizontally, that means it's precisely along the e theta direction, so tangent to a circle of constant radius. E theta is a unit vector, so the coefficient here, v, is precisely the speed. Moreover, but in general, we've got that r dot, vector r dot, is scalar r dot er plus r theta dot e theta. So that tells us that initially, scalar r dot is 0 and r theta dot is v by just comparing the general expression for velocity here with the initial condition that r dot is v e theta. So scalar r dot is 0 means there's no component of velocity in the outwards radial direction. Okay, then the problem tells us to show the particle moves between two heights in the subsequent motion. And so I'm going to eliminate r in terms of z in this case, because z is the height, and it's that I'm interested in the problem. So r is 2 square root of az in general. So solving for r in terms of z. And so r dot is equal to the square root of a over z. Z dot, using the chain rule. And we can substitute all of that into conservation of energy. So conservation of energy implies E is a half times the mass. And then for, so I've got the expression, oh, it's off the top there. So the first term is r dot squared, but I can substitute that is a over z, z dot squared, plus h squared over 4az, plus z dot squared. So that's the kinetic energy term, and now expressed though in terms of z dot. And z plus mgz is the potential energy term. And we know that that's constant. So we can evaluate this at any time that we like, and it's always the same constant. In particular, I can evaluate it at the initial time when I know the initial data. So at the initial time, scalar r dot is 0. We said that above, so also z dot is 0. So this term and this term are 0 initially. And so this is a half m little h squared over 4a squared, putting in z is a initially, plus mga. So this second line I've just evaluated at initial time. And finally, we can also work out this constant little h. Remember that little h is r squared theta dot. That's the definition. I can write that as r times r theta dot. And this is a constant, so I can work out the constant by evaluating it at the initial time. And initially, r is 2a, and r theta dot is v. So that's 2av. So if you substitute that into the equation for energy, so substitute, and then rearrange the conservation of energy equation. So I'm reading this here as this line here, which has got a z dot squared in it, equals the right-hand side, which is a constant. And I solve this for z dot squared. So all the terms with a z dot squared, put those on one side, shove everything else onto the other side, and you get this. So z dot squared is, and a little bit of algebra tells you the right-hand side, is minus 2g over a plus z times z minus v squared over 2g, z minus a. Okay, so that is the conservation of energy equation when you rearrange it for z dot squared. Now notice the following. So this term here is positive. Little g is positive, a is positive, and z is bigger than or equal to 0. Remember, z is a parabola, so it's r squared over 4a. So z is bigger than or equal to 0. So this term is positive, but then there's a minus sign here. On the other hand, on the left-hand side, z dot squared, that's bigger than or equal to 0. So since z dot squared, that's manifestly bigger than or equal to 0, and this first term out here with the minus sign is less than 0, that means that these last two terms must be less than or equal to 0. So we deduce this is less than or equal to 0, and this is a quadratic in z. So it's a quadratic in z, looks like this if you sketch it. And if it's less than or equal to 0, then you must lie between the two roots of the quadratic, and that's z equals a and z equals v squared over 2g. So we can immediately say that the particle stays between heights z equals a and z equals v squared over 2g, which are the two roots of that quadratic. So this shows that the particle, it always moves in some strip around my surface of revolution. So I've not solved for the dynamics, but it does lie always between these two heights. Z equals a is the initial height, right? That's the height that I projected it at. If v squared over 2g is bigger than a, so that's for large velocities, then it always stays above the initial height, okay? Because it's got to lie between this and that one's bigger. On the other hand, if v squared over 2g is smaller than a, so that's for smaller velocities, then it always stays below the original height that I projected it at. And that does make some intuitive sense. Any questions on that before we change topic? Is that all right? So there's quite a bit more. Oh, yeah, there is one, yeah.
First of all, thank you very much. I just want to go back to the first. First of all, I was wondering if you could give us an intuitive reason as to why conservation momentum around the z-axis is constant. And then also, you carefully manoeuvred your way without having to consider the normal force itself.
Yes.
So basically, if we then increase the normal force at various points, does the conservation momentum still, does conservation momentum still hold?
Those are both really great questions. So the first question about conservation of angular momentum, about the z-axis. Yeah, so I was going to make a comment on that, and then I decided not to. But now you've asked, I will. So, so there's a general theorem in dynamics called Noether's theorem. And it says, whenever you've got a symmetry of your dynamics problem, so in our case, that's the rotational symmetry of our surface of revolution. Whenever you've got a symmetry like that, there is always a conserved quantity. And for us, that was the component of angular momentum along the z-axis. But it's a very general theorem, and it's constructive as well. So given the symmetry, it tells you how to find the conserved quantity. Emmy Noether was a female mathematician working in the first third of the 20th century. So she mainly worked in algebra. If you go on and take algebra courses in the second and third year, you'll see Noether's name all over them. But then she also published this result in dynamics in 1918, so exactly 100 years ago, pretty much. And it's a very general theorem, not just in mathematics, but in physics too. And it's played a very prominent role in the development of theoretical physics in the 20th century. I can't possibly give a proof of this because it's in the third year course on classical mechanics. So if you're interested in a sort of deeper answer to why there's a conserved angular momentum, then you should take that course. I think that's the easiest answer to that. Then the second point, yeah, you're asking about the push of the surface. So we could also determine that force. So if you take a dot product of Newton's second law with a normal vector, you'll find an equation for that contact force. And it's just determined, just like it was for the simple pendulum. There's a formula for it. If you want to give an extra push, like someone is banging the surface or something as the particle goes around, then there won't be a conserved energy, because someone is putting in some extra energy. At least the energy we wrote down won't be conserved, that's for sure.
Okay, right. So you require conserved energy in order to have conserved momentum. We needed, in order to prove conserved angular momentum, we needed to have.
No, so they're not directly related. So in this problem, there are both, but they're not directly related to each other. Thanks. Those were great questions. Any other questions? All right, so I was going to start on the next, just briefly on the next topic, but I'm definitely out of time. So tomorrow we're going to change topic, and instead we're going to look at the universal law of gravitation. So we've had many problems now in this course where we're looking at particles acted on by the force of gravity, but that's gravity near to the Earth's surface. There's a much more general universal law of gravitation due to Newton. We'll start that in tomorrow's lecture. And one of the main results of that section will be to show that planets move on elliptical orbits about the sun under that universal law of gravity. So see you then.